Let's discuss parallel and series combinations of resistors. Sometimes it's useful to replace a combination of resistors by a single resistance, or at least try to theoretically find out what's called the equivalent resistance of a circuit or of a circuit branch. So here I have two resistors that are in series, R1 and R2, attached to a battery, which I denote by the tree diagram. And we have to find a single resistor known as R sub S that would replace it. And on the right side, I have R1 and R2 arranged in parallel in the tree diagram. And a single resistor RP is what we need to replace it with. So how do you find out how to get R sub S and R sub P? Let's work with series first. The thing to realize is that current is going to flow from the higher potential to the lower potential by Ohm's law. So this current, whatever current flows through R1 must also flow through R2. So you can think of this as water flowing through a pipe where the pipe has got two different kinds of roughness. You can think of R as roughness. So where it's somewhat rough and where it's much more rough. Well, whether or not the pipe is smooth or rough, if you send water through this end of the pipe, all that water has to come out the other end. So basically, it may flow slower in one pipe than another pipe, and that's measured by the resistance, but the amount of water that comes out must be the same. So that's the big insight. This should be compared with what we had in the series capacitor arrangement, where the charge was the same thanks to the neutral metal island in between. Here, the current's the same because we have this water flowing down the pipe analogy. What about here? You can think of this as a water tank with two different pipes leading to the ground. Well, this pipe has got one kind of slope, or you can think of the slope and roughness to be related. If you have a great slope, it means it's less rough, so water is going to flow fast. If it's very gently sloped, it means it's more rough, and so water is going to flow less. Well, ultimately, regardless of which path the water particle takes, it's going to flow the same height. Whatever water is on the top of the tank is going to end up coming to the bottom of to the ground. So the voltage drop across these are going to be the same. But how about the current? The total current I will definitely split into two parts, I1 and I2. Most of the current is going to take the path of least resistance. The much steeper pipe is going to see a lot more water traffic than the less steep pipe, which will only see a little bit of water. But both of them are going to see some kind of traffic. And then they come down here and recombine to form the full flow into the ground. Now the equivalent circuit will only have the total current I in each case. So now it's just a matter of writing Ohm's law and seeing what Ohm's law tells us. The voltage across this is going to be V1 and the voltage across that is going to be V2. So each of these can be written in terms of Ohm's law. V1 equals I times R1, V2 equals I times R2. And also we have the conservation of energy. V must be equal to V1 plus V2. The total height of the water tower must be equal to the sum of the two heights. Makes common sense. So it's V1 plus V2. Now whatever we have for the resistance, the effective resistance should be I times Rs. So on the left side I'll write I times Rs equals I times R1 plus I times R2. Cancelling out the i's, I get the famous law of addition of series resistances. Rs equals R1 plus R2, and if you have more than 2 then you put and so on. So this is how a bunch of resistors add in series. What about parallel? Let's continue the story for the parallel case. So I've already told you that the current is going to split up into two unequal currents, I1 and I2. But what's the same for both of these is that the amount by which the voltage, that is, drops is going to be the same for both of these. It's going to be V. So by Ohm's law again, I get V equals I1 R1 and V equals I2 R2. And here I'm going to get V equals I times Rp. The operational principle here is that I must be equal to I1 plus I2. Current is conserved, so whatever water comes in here must go here or there. There cannot be any water evaporated or lost. In the same way, whatever electrons or protons flow must split to the left and to the right. There can be nothing that escapes into air, for example. So we need I equals I1 plus I2. So for I, I'm going to write V over Rp. For I1, I'm going to write V over R1. And for I2, I'm going to write V over, from here, V over R2. And this time I'll cancel out the V's instead of cancelling out the I's there. So what will I get? I'll get 1 over R sub P equals 1 over R1 plus 1 over R2. So this is the addition of two resistors in parallel. In general, if you want to add many of them, the most efficient way to do it is to continue this process many times. And after finding the reciprocal, you can invert the result to find the actual resistance. Now, if you compare this story with what we had for capacitors, you will notice an interesting feature. Capacitors and resistors add in the opposite fashion. Capacitors in series added like this. And capacitors in parallel added like this. So in other words, capacitors in series add like resistors in parallel, and resistors in series add like capacitors in parallel. So you got to remember that. In other words, it's okay for you to remember just one of them, remembering that the other one is inverted. Now in this course, you don't have to remember anything because everything is open book, open notes. But if you had an exam where you're allowed to only bring certain number of formulas, that's one way to cut down on the number of formulas you need. Just like we had special formulas for just two capacitors, we're going to have a special formula for the parallel combination with just two resistors. And that special formula is what I'll write here. R sub P equals R1 R2 divided by R1 plus R2. So that's how two resistors will combine. As an illustration of how to find the effective resistance, I would like to solve a simple example. So suppose I have 1 ohm resistors all of them 1 ohm, making life pretty simple. Let's call this terminal A and let's call this terminal B. And here I'll put a 2 ohm resistor. So I want to find the effective resistance between A and B. How will I proceed? Well, you notice that 1, 1 and 2 are all in series. So I can replace them by this formula. So it's going to be 1 plus 1 plus 2 or 4. So I'm going to get the next stage is going to be 1, 1 and 4. That's looking pretty simple. Now 1 and 4 are in parallel, these two. So the effective resistance is going to be 1 times 4, which is 4, divided by 1 plus 4, which is 5, or 4/5. So this is going to be reduced to A and 4/5, which is 0.8. And the last step is to, of course, realize that 1 and 0.8 are in series. So the effective resistance of the circuit between A and B is just 1.8 ohms.